Hi folks, and welcome back to Captain Rod. The purpose of this video is to talk about or demonstrate how to numerically estimate the area under a curve. So what we're going to do here, we're going to take a look at the function y equals x squared, and we're going to try to estimate the area that's bound between this curve, the x-axis, and the line x equals 4. So if I were to highlight it here, we're going to try to estimate that area. Now, the key to area estimations is to break the problem up into small geometries that we know a lot about. This shape here is not some sort of shape that we can very easily calculate the area of. So what we're going to do is we're going to pick a geometry that we can easily calculate the area of. And the geometry I'm going to choose is a rectangle. Now, imagine taking this area here and breaking it into two rectangles here. One maybe looks like this, the other maybe looks like this. First thing to realize here is that, all right, here's my first rectangle here. The area is going to be this height times this height, and you'll notice that that area is going to include this, which is not actually bound under the curve. Same thing with this second rectangle. If I take this height times this height, I'm going to be including an area here that's not actually under the curve. So it's important to realize that how you draw the rectangles really has a big effect on these problems. Not only how you draw them, but how many you draw them, or how many rectangles you draw. Now I'm going to set this up here for now with 4 rectangles. And I'm just going to call the number of rectangles 4. If those rectangles are have even width to them, they have a width equal to what I'm going to call delta x, which would be 1, because the distance from here to here is 4, and I'm dividing this up into 4 rectangles. Each one would have a width 1. Now there's different ways I can draw those rectangles. I'm going to talk about some of the possibilities here. Here's one possible way I could draw those rectangles in this problem. Now I know that the ones I drew don't have perfect even width, but again, don't worry about that for the discussion. An important thing to realize here is that these rectangles again include area that isn't actually bound under the curve. If I go ahead and push this problem forward with the rectangles I have drawn, I'm going to get an estimate for the area that's a little bit too big. That's called in your calculus text, it's probably called an upper bound estimate or something like that. Another potential way to draw the rectangles is kind of bound on the inside. Whoops. I might draw those rectangles maybe like this. 1, 2, 3, and the fourth one actually isn't really technically a rectangle, just a little line there. In this case, you'll notice that there's areas here, 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 and here that are bound under the curve, but they're not going to be calculated from these rectangles, because the rectangles are going to give me this area, and this area. So this calculation with this setup would give me what's called a lower bound estimate for the area under the curve. What I'm going to do here is I'm going to draw the rectangles in such a way that they go through, that the curve goes through the midpoint. So imagine now, a rectangle that maybe looks like this. 1, 2. Now the way I drew this, I can't quite get all 4 of them in there. Just imagine that I can here. Get my 3 and 4. The key concept though is as long as this curve goes through the center of that rectangle, there's a little bit of area included right here that's not under the curve, but it's approximately equal to that area which is under the curve. So if I set my rectangles up like that, I'm going to get an area that isn't a little too big or a little too small. It should be just right. I like to call this the Goldilocks method here, because the area calculated is not too big, not too small, just right. When you look in the textbook here, if you look in a calculus text, it's typically called the midpoint rule. Now, one of the things I'm going to need here to calculate that area, the delta x in this example is 1, because I'm going to use 4 rectangles. And I think I'm going to just modify my picture here to make this look a little more kosher here. Say that 4 is over here somewhere so that I can get a couple more rectangles. My third one and my fourth one. I'm really kind of stretching it to make that picture work, but when you're working numerically, you're always going to need to know the width of these rectangles, and you can always get the width by taking what's called the upper bound, subtract the lower bound, and divide by the number of rectangles. So in this formula that I just wrote out, the b is going to represent the upper bound. In this case, that's this value right here. It's the largest value of x. The a is the lower bound. In this case, that's 0. The n is the number of rectangles. In this case, 4. Now, I'm going to give these rectangles names. I'm going to call this one the first one, this one the second one, the third one, and the fourth one. So we have 4 different rectangles here to calculate the areas for. The area of the first rectangle is going to be, and I'm going to do this in red, that height right there, and then times the width, 1. The area of the second rectangle is going to be this height, and again times 1. Area of the third rectangle is this height, and again times 1. Area of the fourth rectangle is this height, and again times 1. Now to get those heights, we're going to get those from the function values. If you look at, say, the second rectangle here, that red length is the function value at that x coordinate. And this red length is the function value at this x coordinate, and this one's at this x coordinate, and so forth. So the first thing to realize, to even get these areas, we need the appropriate x values to calculate the appropriate lengths. So I'm going to go ahead and calculate those right now. I'm going to call this x1, x2, x3, x4. And here's what those x values are. Again, x1 is this x value right there. So from here to here. x2 is this guy, again, from here to here, and so forth. Now in this problem, the delta x is 1. So that means from here to here is 1. This is only half of that. So the first x value we're going to need is 0.5. I'll go ahead and leave these in red. The second x value, right, so this is 0.5 and then 1 and then 1.5. Second one we need is 1.5. And then 2.5 is the third one. And then 3.5 is the fourth one. So these are the x values we need to calculate the function values at the appropriate places, because we've set this up using the midpoint formula, or the what I call the Goldilocks method. So A1 is going to equal f, whoops, I'm going to do that in black. It's going to equal f of x1 times delta x. And if I actually calculate a value here, f of x1 is going to be 0.5 squared, and the delta x is 1. And I believe 0.5 times 0.5, 0.25. So the first area there is 0.25. Area 2 is going to be f of x2 times delta x. And that's going to be equal to 1.5 squared times 1. Would somebody give me a numerical value? What's 1.5 squared? Two point what? Yeah, okay, that sounds right. 2.25. All right. Area 3 is going to equal f of x3 times delta x. I'm not going to bother writing it down. That's going to be 2.5 squared times 1. Would somebody give me 2.5 squared? 6.25? 6.25. Area 4 is going to equal 3.4 squared times 1. I'm sorry, 3.5 squared. That was supposed to be a 5. 3.5 squared times 1. What's it come to? Thank you, 12.25. The total area we would get by summing these up. So that's going to be 0.25 plus 2.25 plus 6.25 plus 12.25, which equals, would somebody please just run that? What's it come to? which is about 20, which is 21, I guess. So the area bound under this curve should be approximately 21. Now, if you're in a calculus class here, you might know where I'm about to get this, and if you're in my current class, you'll know in a few days how I'm going to come up with this. I know that the exact area under that curve is equal to 4 to the third over 3. Would somebody run that value, please? 4 to the third power divided by 3. 21.33. All right, so this is basically 21.33. You'll notice here that these differ by only 0.33, which out of 21 is a very reasonably small percentage, with only using 4 points. So it's a very powerful method for estimating area under a curve. Now, while I'm at it, I'm going to introduce a little bit of notation here. Okay, so here what we were doing was we were adding up these areas. In the language of calculus, that's called a summation, and there's an actual symbol for it. And this is the Greek letter sigma, which stands for sum. So what we did here is we summed up all of the a sub i's, where I is just an index. If I go back, remember that I labeled these 1, 2, 3, 4. That's what this I is representing, the different values. We summed them up from I equals 1 to 4. So this is called sigma notation. It means sum. This reads sum from I equals 1 to 4 of a sub I. Means, A1 plus A2 plus A3 plus A4. So again, this video is just meant to be kind of an introduction into how to estimate areas. I'm going to go ahead and just stop this right now and make another one. I hope this gives you a reasonable flavor for it. Have a nice day.